Hi guys, in this lesson we'll take a look at the non-isothermal reactors. So a non-isothermal behaviour has a profound effect on the product distribution when several reactions are involved. So thus far in our course we've only considered isothermal reactors. So here the response of the different reactions are dependent on both the temperature and the concentration, but at different rates depending on the activation energy and the frequency factors. So here what we can't assume is that we have a constant temperature within the entire system, and that the concentration will vary depending on the different activation energies. Now the term non-isothermal is used to indicate that there is a change in the temperature as a result of the chemical reaction. So when we talk about isothermal reactions, then if we take a typical enthalpy chart, so for activation energy, then say here this is our EA, so activation energy here. Then what we would do is we would say that if this is an exothermic reaction, then of course heat would be given into the system. So our reactor, if we have a reactor here, then this reaction would begin to overheat. Now on isothermal conditions we assume that the rate of heat generation is equal to the rate of the heat leaving the system. So what we can do here is we can apply a jacket around the reactor. Now when we assume non-isothermal conditions, this is a more realistic approach because there will be spots within this reactor in which they aren't a uniform temperature distribution. So this is just taking into account these hot spots within the system. Now in the case of a batch reactor, it would mean that the temperature of the reactor would vary with time, while the case of perfectly mixed continuous flow reactors, it would indicate that the reactor temperature and that of the products are different from the inlet temperature. So what we would say here is that the temperature, if this was a CSTR, then the temperature here would be T0 and T1 would be the outlet temperature. So what we would then say is for isothermal conditions that T0 would be equal to T1, whereas in non-isothermal conditions we can't assume that hypothesis. So the reactors to be considered within this course would be non-isothermal batch and non-isothermal CSTRs. Now in this lesson we'll only consider the non-isothermal batch reactor. Now the non-isothermal plug flow is similar to the non-isothermal fixed bed catalytic reactor, and we got into the design equations and how we develop these in our online course, so be sure to check that one out. I'll put a link in the description to the website and the course. So we go into the details on how to model fixed bed catalytic reactors as well. So when discussing the non-isothermal batch reactor and CSTR, then the reactor contents are considered to be homogeneous, and that the state of perfect mixing is assumed to exist. So therefore what we assume here is that they are in the same state. We can't assume that for fixed bed catalytic reactors because we can have suspension systems. So here we'll take a look at the non-isothermal batch reactor modelling. So if we consider the mass balance, then the rate expression, so minus RA, is equal to minus dCA over dt. So this is the change in the concentration with respect to time. Now minus indicates that the concentration can be either increasing or decreasing depending on if we're talking about a reactant or a product. So in the form of a reactant, of course the amount of the reactants will decrease over time, so that's where the minus comes into play. Now if we want to write this in terms of the conversion, so X, then what we do here is we relate the conversion X to the initial concentration. So we can then take the initial concentration out of our integration because this isn't going to change. This is the initial concentration, so this is constant. And then what we model is that the change in the conversion with respect to time. So we can see that as the conversion changes, what is the effect on the overall reaction rate. Now if we take a look at the energy balance, then the overall general balance is that the accumulation is equal to the amount of energy in, so usually enthalpy in minus enthalpy out, plus or minus energy transfer, plus or minus heat from the reaction, and plus or minus the work. Now in most cases the work done on the system would be negligible, so therefore we could cancel this out. Compared to the heat effects, this value would be considerably small, so we can just neglect this term. So that means that we can rewrite this as dH over dt, so this is a change in the enthalpy with respect to time, is equal to the density multiplied by the volume multiplied by Cp, so the specific heat capacity, multiplied by the change in the temperature with respect to time. So then that means, so this is the accumulation term, so we have rho v Cp dt over dt is equal to the enthalpy in minus the enthalpy out, plus or minus Q, so this is energy transfer, plus or minus the heat of reaction, and then multiplied by the minus Ra, so if it's with respect to A, this would be minus Ra in here, multiplied by the volume. So this entire term here is the heat from the reaction. Now Q would be positive for heat transfer to the reactor. So if we have a reactor system here, then if we have heat entering the system, then Q is positive. If we have heat leaving the system, Q is negative. Because what we say is that this concerns ourselves with this system. So if we add in extra heat, we of course have to add the value of Q. If we are losing the value of Q, we have to make it a negative. Now for batch reactors, because there's no flow in or out of the system, the above equation that we've seen, we can neglect the enthalpy in and the enthalpy out. So this would dissolve to rho Vcp dt by dt is equal to Q plus or minus delta HR minus Ra multiplied by V. So this is a simplified algebraic relation, and we will look at a special case in our course. So again, be sure to check that one out, and we'll have a look at the special case for adiabatic operations, whereby adiabatic takes into account the value of Q, so whether heat is coming into the system or leaving the system. So that's the end of this lesson. Thanks for watching. Hopefully this has improved your understanding of the modelling of non-isothermal batch reactors. If you like this video, please like and subscribe to the channel. Also check out our online course for up to 50% discount, and by subscribing to our website you get free access to our online resource library, which contains over 20 reference texts absolutely free, so be sure to check that one out, and we'll see you in the next video.